Alright, here we are looking at review problems. And though I didn't include number 32, it's a pretty good problem. So let's just take a peek at number 32 together for those people who watch the videos and get a little help from them. So, in number 32, let me get my vector arrows again here. Okay. Number 32, you kick a stone over the edge of a cliff at 18 meters per second, and we know that the cliff is 52 meters tall. So I'll make that this red line here. Hey, draw the line. 52 meters tall. How long does it take for the stone to fall into the water? Well, this is a good projectile question. You're going to then use this. You're going to take delta y. That's the 52 meters. And you're going to use that to find the time in the problem. You're going to use our equation where delta y equals 1/2 gt squared. Using your 52 meters, you can find the time of fall. With the time of fall, ideally I would say, how far out does it land? But that does not appear to be a question that they're asking. I would ask that if I was writing it. And I'd take the time of fall I find. Let's see, 52 meters, divide by that. Whatever the square root of 10 is, so that's going to be, 3 seconds or something like that. So you're going to take your roughly 3 seconds or whatever times the 18 meters per second, which is the horizontal velocity given in the problem. You take those, multiply them, and it'll tell you how far out it would land. Although that's not what the book's asking. It's still a good question. So that's 32. Looking at number 34 here. 34. A shell is fired from the ground with an initial speed of 1.7 times 10 to the third meters per second. So that's 1700 meters per second. With an angle of 55 degrees to the horizon, neglecting air resistance. Find the shell's horizontal range and find the amount of time it is motion. Alright. So this one's a bit problematic. Let's look at our equations real quick here. Not there. Looking here. What we know VI, we know the angle. We want to find delta x, we want to find the time of fall. Well, problem being, if we come here to these equations and we look here, if we want delta x and t, we have to do that in 2 steps. What I would recommend is come forward, use this here range equation, put in the VI, 1700, put in the angle, 55, calculate that out, and you're going to get some horizontal distance. It's going to be pretty big. I mean, this thing's moving fast. Then I take that delta x, come back 1 page of notes, take the delta x, put it in right here, use the 1700, use the cosine of the 55, and find the time. If you wanted to take a different route from there, I would say use this one here, find the height. With the height, I'm sorry, you don't even need to do that. Use at the halfway point here, put in a 0, the initial velocity, the angle, find half of the time, and multiply by 2, then put that time in down here. So those are the 2 ways I do it. I'd either use this one to find half of the time, this right here, why is it doing that? This right here to find half the time, and then double it, and then put that in down here to find the displacement. So that's 34. 37, this one's a complex problem. Here's what I want you to be able to figure out with this problem. I want you to figure out the maximum height of the projectile. I want you to find delta y. I also want you to find the overall horizontal displacement of this projectile. Again, looking back at our equations, we can use this one here, use VI, use sine and cosine of the, in this case, 75 degrees with the very fast velocity here. If I'm looking here, it looks like 250 meters per second. So put your 250 in, put your 75 here and here. Find the horizontal range. So I do that. Then you could do a couple different things. I guess it doesn't have to be in that order, but it doesn't matter. How high up do you go? You're looking at delta y. Use this equation like we've been using to find the maximum height. Then when they say how close to the enemy ship does it come, you could just take the The distance is given in the problem and subtract and tell me how much you missed the ship by. What I care is that you calculate where the thing lands. And when it comes to missing the mountain, well, you could take the, here's this kind of crazy thing. If you put in the problem, it advertises 250, oh, I'm sorry, 2.5 times 10 to the third, so 2,500 meters as the distance horizontally to the peak of the mountain. If you put that in, and you put VI, you put the cosine, you're going to get the time it takes to get over top of the peak of the hill. You could then put that time in here and here and get the height of it, but I'm not asking you to do that. In review, what I want you to do with this problem is find the maximum height of the projectile and find the horizontal range of the projectile. If you do those two things, you can do everything I want you to do with this. Alright, let's squeeze in one more question here. Let's squeeze in number 38. Explain the statement, all motion is relative. And when I say all motion is relative, it's that whole thing we talked about in class where it's from your perspective. We look at the bombardier. If you're looking down through the drop door on the bomber, it looks like the bombs are falling straight down. But if you're standing on the ground watching the bomber go by, it looks like the bombs are moving forward and down. That's what we're talking about, relative motion. It's all in comparison to a frame of reference. Typically, the frame of reference is the world around you. Just saying.